Hello learners, and welcome to a video tutorial on resonance in an open tube. So here we've got a tube of length L, and what I've drawn here is I've drawn it resonating at its fundamental frequency. So here's what's happening. This is a sort of representation of the displacement of air inside the tube. So here at this position, there is no displacement of air. That air is remaining in that spot. But this air is actually displacing out of the tube. And so if I were to draw this as to show kind of the representation of the pressure inside this tube, well, at each end, that's where I have the fastest moving air, so I would have the lowest amount of pressure. And inside the center, it's stationary, and that air is being compressed in there, so it's actually at the highest pressure. So it would look something like this. So this bottom drawing represents the displacement of air, and this top drawing represents the pressure. Both of these represent the fundamental frequency, and we can utilize this to figure out, okay, well, what is going to cause a tube of a certain length to resonate? What frequency? So if I look at this, I've got an antinode, and then a node, and then an antinode. So the distance between an antinode and a node is 1/4 wavelength, which means to get all the way across the tube, that is half a wavelength. So the wavelength of what is resonating in here, the fundamental wavelength of this tube, would actually be equal to 2L. Because if I go all the way across, I get 1/2 lambda, so I would have to go all the way back across to get to lambda. So that's 2L to get this thing to resonate. Now, why is this important? Well, if you look at a wind chime, you've got all of these tubes that are different lengths. Or if you look at, Peter Pan's flute that he's playing with or whatever, all of your tubes are at different lengths L. And the reason is you don't want a bunch of tubes clanging around just making the same note. You want to have a very nice, harmonious, peaceful sounding wind chime. So you have these tubes cut to different lengths, which means they all have a different fundamental frequency. And so when whatever's bouncing around in between the tubes knocks into one of them, it will vibrate at its fundamental frequency. So you can use that wavelength, and you know that velocity equals frequency times wavelength. The speed of sound is just going to be the speed of sound. So that remains the same for all the tubes. So what you change is the length, which changes the wavelength. If that stays fixed, if you change the length, that means you change the frequency, which means you change the note that you hear. Higher frequency means a higher pitched noise. So to get a higher frequency, you would need a shorter tube. So here, I've got a glass tube that is a certain length, and I'm going to actually get it to resonate. So take a listen. How nice is that? So it took a certain wavelength or certain frequency of tuning fork to get the tube to resonate. So I'm causing the vibration out here, which causes the tube to resonate inside. And we get a really nice sound. Now how neat is that?